Good afternoon, dear learners. This is your chemistry tutor, Charles Kwame Bando, handling the general chemistry course. The code is EBS132, and as I have been telling you, this course is being handled with myself and then Mr. Amako, Stephen Kwame Amako. And this is the unit 4, and in unit 4 we are definitely looking at chemical formula and then equations. But before we start whatever we are supposed to do, I will urge you to make sure that you obey all the protocols that our dear president has put forward that we should follow, so that at least you save yourself and save others as well. And so you know that the COVID-19 is very real, and as you move about, if you don't have anything so urgent and so important to do, I wish that you stay home. And then whenever there's the need to go out, you go with your face mask and then sanitizers as well. Please, your life is very much important and dear to us. So try as much as possible to obey these protocols. The washing of hands, wearing of face masks, and then social distancing and the rest. So that when all is set and when everything calms down, then we'll meet together and then go on with life as it's supposed to be. Thank you very much for your attention as far as this is concerned. Alright, so let's look at what we have for the day. And before we continue, we want to look at our performance indicators. In those days we call it specific objectives or objectives, but now we are only calling it performance indicators. And so by the end of this lesson, you, the learner, should be able to use the periodic table to illustrate symbols representing their respective elements. For instance, magnesium, if you see Mg, you should know that it represents magnesium. If you see Al, you should know that it represents aluminum. If you see sodium, Na. If you see H, you should know that the H represents hydrogen. There are a lot of them. Like if you see K, you must know that it represents potassium and all of that. Alright. Now you should also be able to indicate the symbols indicates that the symbols represent the atoms of an element, and write the formula of 4 common compounds, and then outline the steps involved in writing a chemical equation, and then also write a balanced chemical equation for a simple reaction. Right? And then also to indicate symbols like G for gas, L for liquid, S for solid, AQ for that is aqueous, that is a solution or any compound that is being dissolved in water, that to denote the states of a substance in an equation. So mostly in any chemical equation there is the need to show the various states of the compounds that are forming the equation. So if you see S attached to any compound, that means that compound in the equation is in its solid form and all of that. So at the end of this lesson, if we're able to come out with these steps, then we will say to ourselves, learning has really occurred. And if not, then of course we have to revisit the lesson again. Right. Alright, so we are looking at non-binary compounds. We have looked at compounds that contain 2 atoms only. This time we are looking at compound which contains more than 2 atoms. So the non-binary compound, that is what we are going to look at, how we can write their chemical formula. So for example, I said I write the symbols of the elements, so the metal and then the radical involved. Right, so we have what we call the radicals, like those anions that are consisting of two or more atoms. So for instance, SO4 2 minus is a radical. So a group of atoms that carries a charge, they are known as radicals. You can have like CO3 2 minus is also a radical. So the first step in doing that is write the symbol of the metallic element and also the radical, just like the one we did for the binary compound. So this time when a metal is bonded with a radical, you have to write the symbols involved first, like this. So for example, a bond between sodium and then the carbonate compound. So I have my symbol for sodium, which is Na, and then I have carbonate, which is CO3. Then the next step is to write their valences, to write their or indicate the valences below them. Now I know by now for valency of sodium it is very simple, so you easily write it as 1. Then how do we know the valency of carbonate compound? How do we know? I want to ask and put before you if you can tell us. Good. So a short way or a simple way by which you can know this is, first and foremost, consider the number of electrons in the outermost shell of carbon, which we know by now it is 4. I hope by now you know that carbon is number 6 on the periodic table, and so the first shell taken to the second shell will take 4, and so carbon goes into that bond with 4 electrons. But then we have 3 atoms of oxygen, and each of them require 2 electrons to be full. And so if carbon should give 4, whereas the 3 oxygen atoms also need 6, then there will be additional 2 electrons that this CO3 bond will need to be or to become complete. And so whoever is going into that bond should provide the 2 electrons. Right? Just like a family who has set up a bride price upon a woman, that if you want to marry this woman, this is what you must pay. Just like Jacob, who wanted to marry Rahel, and so he had to serve for 7 years. So whoever is coming to form a bond with carbonate compound, CO3, should provide the 2 electrons, right? And so by now the 2 electrons that bond will need to be complete becomes their valency. And so the valencies are 1 and 2, 1 for sodium and 2 for the carbonate compound. Good. I hope it is clear to you. And so because of this, we do go ahead with our next step, which is the interchanging of the valencies, and we write them as subscript. So we do the interchange. We give 2 for sodium, and then we give 1 also to carbonate compound. And this we have Na2CO3. Na2CO3. What it means is that sodium has 1 electron in its atomist shell, but the CO3 is also looking for 2. So one sodium atom cannot satisfy the condition for under which such a marriage will be performed. So you have to go for another brother sodium, so that the 2 will get their monies together and they pay the price. So that is why we have 2 sodium atoms coming together to donate 2 electrons to satisfy the 2 electrons that the CO3 needs. So the bond is Na2CO3. So 1 molecule of sodium carbonate or sodium triosocarbonate 4 contains 2 atoms of sodium, an atom of carbon, and 3 atoms of oxygen. Okay, I hope this is also very simple for you. Right. Now let's look at another example. another example. So we will go through the same process. Now we have aluminum, we have sulfate. So we have written the symbols. Now the next thing is writing the how do I say, the valences. Now for aluminum, we already know the valency from the previous slide that it is 3. But how do we know that of sulfate? Now the same process that we went through to know for the carbonate, we go through the same thing. And so here again, sulfur has 6 electrons. It is number 16 on the periodic table, and its outermost shell has 6 electrons. And so if sulfur is bonding with 4 atoms of oxygen, it will go with 6 electrons. However, these 4 atoms of oxygen also need 8 electrons, and so when they share the 6, there will be additional 2 electrons that they will need, and that 2 electrons that they will need to form or to be complete becomes their valency. So we are also saying that the valency of SO4 is also 2. So let's see how aluminum and sulfate are going to form their bond. Good. So we have 3 against 2, and as usual we do our interchange. And so we give 2 to aluminum and 3 to sulfate. Good. This is how the formula is being written. So we have Al2SO4 all in bracket, and the 3 comes out. You see, there is a possibility for you to just add the 3 to 4 and write Al2SO4 7. Somebody will also just multiply and have Al2SO4 12. Right. So whatever you think and how you think about, if it were to be an objective test that want to test you and see how you understand what you are doing, we could have just provided you with all the thoughts that will come to your mind. Don't forget that any examiner has also been a student before, so whatever thought that you will have, he or she might have also gotten it already. So this is how we have to write it. So Al2, then you open a bracket, SO4, you close the bracket, and so that 3 is for all of SO4. Good. And so with this, 1 molecule of aluminium tetraoxosulfate 6 contain 2 atoms of aluminium, 1 atom of sulfur. Let me put it simple way. That is 3 atoms of sulfate. So 3 molecules of the sulfate. Let me take it again. 1 molecule of aluminium tetraoxosulfate 6 contain 2 atoms of aluminium, 3 atoms of sulfur, and then 12 atoms of oxygen. Good. What it means is that you need 2 aluminum atoms to provide 6 electrons, which will be shared by 3 molecules of SO4, and that is why we have the formula as such. Good. So I believe by now you are very conversant with writing of these chemical formulas. You are very conversant with writing of this chemical formula. Please, if not, try and go through the process again. Then you move on to something else that we are going to look at. Good. So these are trial questions. Don't be bothered so much with the trial questions that have been given to you. See, don't call yourself a master on what you have not practiced. So when you're able to practice these ones and then come out successfully, then you call yourself a master as far as writing of chemical formulas are concerned. Good. And so we have given you aluminum hydroxide, calcium nitrate, calcium hydroxide, and then potassium phosphate. So you should know the phosphate, you should know the hydroxide radical, you should know the nitrate radical, you should know. So when you know this, you can easily write the formula. Of course, potassium, calcium, aluminum, their balances are very easy to be determined, but that of phosphate, nitrate, and hydroxide, use the same approach that we have done so far, and it will be very easy for you. I hope you will be able to do a good job for me. If you are not able to do from here, please do not go further. Just go back, learn again, and then come and continue. Alright. Now, moving a bit away from chemical formula, we are now going into chemical equations. Of course, in every chemical equation, apart from the word equation that may be given to you, there is also the need to write the equation in symbol form. Right. So we are saying the chemical equation is an equation which expresses in symbols the various elements or compounds reacting to form a new substances, reacting to form new substances or a new substance. Good. So a chemical equation is nothing but equation which expresses in symbols various elements or compounds reacting to form new ones. Right. So sometimes you can have the word equation, then you produce it in the symbol form, or the equation can be given in sentence form. It is up to you to write it. So it's like somebody can say sodium hydroxide reacted with, sodium hydrochloric acid. Let me take it again. Sodium hydroxide react with hydrochloric acid to form salt and water. Write a balanced equation to show the reaction. If you don't know the formation of or how to write chemical formula, you cannot move on to that stage. That is why we have done the chemical formula writing, so that when we are now applying it inside the writing of chemical equations, we will do a very good job. Alright. Good. Now we also adding the chemical equations, the statement in formula that expresses what? Identities, quantities of substances involved in a chemical or physical change. It is also a shorthand notation for a chemical reaction. Very soon we'll look at chemical reactions, but we are saying that chemical equations are, well, shorthand notation for a chemical reaction. Right. So it's just a statement in formula that expresses what? Identities and quantities of substances involved in a chemical or physical change. Okay. Now we also want to this is very important. Note that when chemical reactions occur, atoms are neither created nor destroyed. Atoms are neither created nor destroyed. You may decide to call this conservation of atoms, but what we want to say is that atoms are neither destroyed nor created in chemical reactions. Right, so if I have H2 plus O2 giving me H2O, I have not, so on the other side you have one atom of oxygen, on the other side I have two atoms of oxygen. So will you say that one atom of oxygen is destroyed? No. What is happening that you have to do what you call balancing of the equation, which we will do in later slides. So we are saying that atoms are not created nor destroyed in a chemical reaction. This means that when you write a chemical equation, there must be the same number of each type of atom present in the reactant and the product. Good. So we will very soon look at what we mean by reactant, what we mean by product. But what is happening that in every equation that we write, which is a chemical equation, the right hand side, the number of atoms there should be equal to the number of atoms at the left hand side. That's what we mean by atoms are not destroyed nor created. So you have to make sure you have equal numbers in each side. Alright. Good. Now this is an illustration of, or a general illustration of a chemical equation. So I have A plus B matching up, giving us C plus D. A plus B giving us C plus D. So A plus B means they are the starting substances or the reacting chemicals, and they will give you what we call the product. So in any equation, you look at the direction of the arrow to know what the reactant are and the product. I can just interchange the direction of the arrow. When I do that, and then the arrowhead now points to my left, then in this case C and D becomes your reactant. So the most important thing is the direction of the arrowhead. So when where the arrow points to is where we have the product, right? Now we are also adding the chemical equation. Give us the following information. Once we see a chemical equation, we should know the reactant, we should know the products, we should know the state, the physical state of the reactor, like we said, gas, whether they are in gaseous state, solid state, liquid states. Now the feasibility of the reaction. See, there are some atoms who don't react. For instance, there is something we look at that we call the reactivity series. So in that series, there are elements who cannot react with certain compounds. Right? We'll look at that, so I wouldn't want to bother you. So we look at the probability that the reaction can occur, and also the solvent and then the experimental condition. There are some of the reactions that will need heat to be able to occur. Some will need what you call the catalyst. There are a lot of conditions under which reactions. So a chemical reaction should give us some of these, if either all or some of them. Alright. Alright, so we are going to look at what we mean by word equation. Word equation, right? So we are saying that word equation should state the reactant, that is the starting materials. It should also give us the ending materials, and then the direction in a form that, so a direction of the reaction in a form that could be used to write what? A chemical equation. That could be used to write a chemical equation, right? So this is very, very, very important, right? Good. So as an example, if I have hydrogen gas plus oxygen gas, this is giving me what? Water vapor. This is a complete word equation. And you could see the gas, so you could see the direction of the arrow pointing to water vapor. So in this case, hydrogen gas and oxygen gas are the starting materials, and then the water vapor becomes the ending material, right? Okay. So look at the equation, the chemical equation. So I have my H2 gas, O2 gas, giving us H2O also gas. And that is the chemical reaction or the chemical equation. And so with it, the others are just balancing of the equation. Balancing of the equation. Okay. Another one is copper plus oxygen, giving us what? Copper 2 oxide. That is a word equation. See, we are writing copper 2 because copper has what we call double oxidation state. We can have copper 1 or copper 2. So if we have to specify, alright, if we don't specify, then you have to write the equation in all the two forms of copper. But once it's been specified, then you have no option than to write it as it is. Okay, so I have my Cu plus O2, and that will, because it's copper 2, I will only have CuO. Then all the others are just balancing of the equation. Okay, so that is how we mean by word equation, and then transferring the word equation into a chemical equation or reaction. Alright. Good. In fact, we are also going to look at how we can balance chemical equation. How we can balance a chemical equation. If a chemical equation is given to us, how do we make sure that, since atoms are neither created nor destroyed, how do we make sure that whatever we have at the product side will be equal to what we have at the reactant side? So try as much as possible and pay attention here. We are going to watch this video that we picked, and then at the end of the day you will understand. The video will help us to appreciate balancing of chemical equation. So let's watch the video and we'll come back.
Is one of those concepts in chemistry that often confuses people. But I think if we will see that if we work through this carefully and methodically, and we also appreciate the art of balancing chemical equations, that it's actually not too bad. So first of all, what is a chemical equation? Well, this is a chemical equation right over here. It's describing a reaction. So if I take an atom of aluminum and I add it to a dioxygen molecule, so a molecule that has two oxygens with it, under the appropriate conditions, they will react to form aluminum oxide. And the aluminum oxide molecule has 2 aluminum atoms and 3 oxygen atoms. And so you might say, okay, well, what's the balancing business all about? I have a chemical reaction. What do I have to balance? Well, if you look carefully, you might notice that you don't have the same number of each atom on both sides. So, for example, right over here on the left-hand side, how many aluminums do we have? Well, on the left-hand side, we have 1 aluminum. How many do we have on the right-hand side? Well, on the right-hand side, we have 2 aluminums. And so aluminum just can't appear out of thin air by virtue of some magical reaction. You have to have the same amount of aluminums on both sides, and the same thing is true for the oxygens. Over here on the left-hand side, we have 2 oxygens. They form 1 dioxygen molecule, but that has 2 oxygen atoms. And then over here in the aluminum oxide molecule, we have 3. We have 3 oxygen atoms. So once again, we can't just have miraculously an oxygen atom appear out of nowhere. So we have to balance the number of aluminums on both sides. This number and this number should be the same. And we have to balance the number of oxygens. This number and that number should be the same. So how do we do that? Well, one thing might be to say, okay, if I've got 2 aluminums here and I have 1 aluminum here, well, why don't I just double the number of aluminums right over here? So I could just write a 2 in front of it. So now this says 2 aluminums, so I no longer have 1 aluminum here. I now have 2 aluminums. And so it looks like the aluminums are balanced, and they are indeed balanced. But still we have an issue with the oxygens. Over here I have 2 oxygens. Over here I have 3 oxygens. So one thing that you might say is, okay, well, how do I go from 2 to 3? I could multiply by 1.5. So I could multiply by 1.5. And if I multiply 1.5 times 2, well, that's going to be 3. So now I have 3 oxygen atoms on this side and 3 oxygen atoms on this side. But the convention is that we don't like writing 1.5 molecules. We don't like having this notion of a half molecule, which is kind of this bizarre notion. We want whole number molecules. So what can we do? Well, you can imagine, and this makes it very similar to what you did in algebra. An algebraic equation is we just can multiply both sides by the same number that gets rid of having this fraction or this decimal here. So if we multiplied both sides by 2, we're going to do that. This is going to be a 4, this is going to be a 3, this is going to be a 2 right over here. So let me do that. Let me multiply both sides by 2. So instead of 2 aluminum atoms, let me have 4 aluminum. Actually, let me just write the chemical equation first in the form that it was before. So I had aluminum plus dioxygen, a molecule of 2 oxygens, yielding in the reaction. These are the reactants. This is the product. Aluminum, aluminum, aluminum oxide. So what I'm saying here is to get rid of this 1.5, to turn it into a whole number, let's multiply all of these, all of the number of molecules by 2. And here there's implicitly a 1. Let me do this in a different color. There is implicitly a 1 right over here. So let's multiply all of these by 2. So 2 times 2 is, let me do that same color. 2 times 2 is 4. That's not the same color. 2 times 2 is 4. 1.5 times 2 is 3. And then 1 times 2 is 2. And now you can verify. How many aluminums do we have on each side? Well, I have 4 aluminum atoms on the left-hand side, And how many do I have on the right-hand side? I have 4 aluminum atoms. How many oxygens do I have on the left-hand side? I have 3 molecules of dioxygen. Each molecule has 2 oxygen atoms, so I have 6 oxygens on the left, and I have 2 times 3 oxygens on the right, or I have 6 oxygens. So my chemical equation is now balanced.
Alright, so I believe you have enjoyed the video. So we are saying that a balanced equation is an equation in which the total number of atoms of each element on both sides of the equation is what? Equal. So you saw that in the reaction of aluminum and oxygen, we have an atom of aluminum plus 2 or let's say 2 atoms of the oxygen, that's the O2, giving us Al2O3, as we saw earlier in the writing of our chemical formula. And so what happens was that there was the need to, balance that particular equation, and you saw the process that it went through. We'll look at balancing further. Alright. Okay. Now there is this also another video, so let me also allow you to watch this video as well. Then after the video, I now move on to talk about what I want to talk about, but the video will help us to get a concept more right.
Hello and welcome to Chemistry Solutions. This tutorial is on balancing chemical equations. In a chemical reaction, atoms are neither created or destroyed, so this means that a chemical equation must have an equal number of each type of atom on both sides of the reaction arrow. We'll start out balancing chemical equations by balancing the elements that occur in only one compound on each side of the equation. Now remember, when balancing chemical equations, you can only change the coefficients in front of the reactants or products in a chemical reaction. You can never change the subscript. If you change the subscript, you're actually changing the identity of the compound. Let's take a look at an example and try balancing this equation. Before we start, we're going to want to take an inventory of how many of each type of atom are on each side of our reaction arrow. So on the reactant side, we have 1 carbon atom, 4 hydrogen atoms, and 2 chlorine atoms. On the product side of our chemical equation, we have 1 carbon atom, 1 hydrogen atom, and 5 chlorine atoms. Now looking at this equation, because we have 1 carbon atom on the reactant side and 1 carbon atom on the product side, carbon is already balanced. So our next step would be to balance the number of hydrogen atoms, and I'm choosing to start with hydrogen because hydrogen occurs in 1 compound on the reactant side, CH4, and 1 compound on the product side, HCl. In order to balance the number of hydrogens on the product side, we're going to want to put a 4 coefficient in front of HCl. Remember, we can only add coefficients, we can never change subscripts. Now if we count up the number of each type of atom we have on both sides, you'll see that we still have 1 carbon atom on both the reactant side and the product side, but now we have 4 hydrogen atoms on the reactant side and 4 hydrogen atoms on the product side. But by putting a 4 coefficient in front of HCl on our product side, we not only have increased the number of hydrogen atoms on our product side, but we've increased the number of chlorine atoms on our product side as well. So if we look at our new total, we still have 1 carbon atom on our product side, but we now have 4 hydrogen atoms, and we now have 8 total chlorine atoms. 4 from the CCl4 that we had to begin with, and 4 from our 4 molecules of HCl. If we compare the types and numbers of atoms that we have on the reactant side and the product side now, we'll see that we still have 1 carbon atom on each side, we have 4 hydrogen atoms on each side, but on our product side we have 8 chlorine atoms, and on our reactant side we only have 2 chlorine atoms. So in order to balance our chlorine, we're going to add a 4 coefficient in front of our Cl2 molecule. And if we have 4 molecules of Cl2, that now means that we have 8 chlorine atoms on our reactant side. And remember, I chose to add 4 as the coefficient in front of Cl2 because each molecule of Cl2 has 2 chlorine atoms. So if I have 4 molecules of Cl2, that gives me a total of 8 chlorine atoms, which I found just by multiplying 4 times 2. And now that we have the same number of each type of atom on the left side of our reaction arrow and the right side of our reaction arrow, we can consider this reaction correctly balanced. And after you feel that you've correctly balanced your chemical equation, the last thing to check is that your coefficients, which would be a 1 here, we don't typically write, 4, 1, and 4 are in their lowest ratio. Having coefficients that aren't in a lowest ratio does not make the chemical equation incorrect, but typically instructors and classes are looking for the lowest ratio when considering a balanced equation. And typically when balancing your equation using this method, you will come up with the lowest ratio. But it's just one more thing to keep in mind. Let's take a look at another example. Again, I'm going to start by taking inventory of how many of each type of atom I have on the reactant side and the product side. On the reactant side, I have 4 phosphorus atoms, 11 oxygen atoms, 10 from the molecule P4O10, and 1 from the molecule H2O, giving me a total of 11, and 2 hydrogen atoms. On the product side, I have 1 phosphorus atom, 4 oxygen atoms, and 3 hydrogen atoms. Let's start by balancing the number of phosphorus atoms. And again, I'm choosing phosphorus because it occurs in 1 compound on the reactant side and 1 compound on the product side. And it seems to be, if you follow this method, it'll make balancing the reaction a little bit easier. But you can really balance whichever type of atom you prefer first. Because I have 4 phosphorus atoms on my reactant side, I know that I need 4 phosphorus atoms on my product side. And because I can't change the subscripts of any atom, I have to add my 4 as a coefficient in front of the molecule H3PO4. By adding 4 as my coefficient in front of H3PO4, I have not only now changed the number of phosphorus atoms I have, but I've also changed the number of oxygen atoms and hydrogen atoms. So to determine the number of oxygen atoms I now have on the product side, I multiply the coefficient by the subscript on the oxygen, which gives me 16. And to determine the number of hydrogen atoms I have on the product side, I multiply the coefficient by the subscript on the hydrogen, which gives me 12 hydrogen atoms. Now that I've balanced the number of phosphorus atoms on the reactants and product side, I'm going to balance the number of hydrogen atoms next. So using the new number of atoms that I've calculated, I have 12 hydrogen atoms on my product side. In order to give me 12 hydrogen atoms on my reactant side, I know that I'm going to need to add 6 as a coefficient in front of H2O. So 6 times the subscript on H, which is 2, now gives me 12 hydrogen atoms on my reactant side. But again, because I put a coefficient in front of the entire molecule, I've not only changed the number of hydrogens on the reactant side, but I've also changed the number of oxygens. I now have my original 10 oxygens from the compound P4O10, but I have an additional 6 oxygens because I have 6 H2O molecules, which gives me a total of 16. Now you can see in this case, balancing our hydrogen automatically balanced the number of oxygen atoms on the reactants and product side. This isn't always the case. Sometimes you need to go balance that third type of atom, but sometimes you'll be fortunate enough that it will just work out and save you a little less work. And now because I have the same number of each type of atom on the reactant side and the product side, I can consider this reaction correctly balanced. Thanks for listening to Chemistry Solutions.
Good. So I believe the video has done us a lot of good, right? So try to, study it very well. It's very informative. So it gives us a lot of insight into balancing of the equations. Okay, so let's look at an example which we have also given here. How do we balance this equation? But before we even go into balancing, the question is this particular equation balanced? Right, so you need to take inventory as we saw in the video. Right, when that is done, you see what to do. So we are saying that symbols that AQS, S, S, L, G, they are all telling you the various states of the substances in the equation, right? Now we are saying that the above equation is balanced because the total number of atoms on each element on the left hand side is equal to the total number of atoms on the left, so on the same on the right hand side, right? So if I look at this, I have 2 atoms of sodium on the reactant side and 2 at the product side. For hydrogen, 2 reactant side, 2 product side. Oxygen 3, chlorine 2, and then carbon 1. And so when you look at this inventory, it is only telling us that the equation is well balanced. Equation is well balanced, right? So that is how we check whether the equation is balanced or not. If you check and it's not, then you have to make sure you do the right thing. All right. So let's look at this particular equation, having in mind what we have learned in the video. If you were to be with me in class, I would have asked you to write what you have learned or what you learned from the video. But even now, you can still do that, right? Okay, so let's study this particular equation and see whether it is balanced or not, right? So we are saying that this equation is balanced. Why? Because the total number of atoms on each element on the left side is equal to the number in the right side. So when we take inventory of the equation above, this is what we are going to have. We are going to have Na2 here, 2 at the left, 2 at the right. Hydrogen 2 right, 2 left. Oxygen 3 right, 3 left. Chlorine 2 right, 2 left. Carbon 1 right, and then 1 at the left side. And so this will tell you that the equation is well balanced. So anytime an equation is, sometimes the equation itself will be balanced, but the examiner will tell you balance the equation below, and you'll be tempted to think that it's not balanced, and so you only start by just writing some things down. But so anytime you want to balance the equation, the very first thing you need to do is to take inventory of the equation before you start your balancing. Alright, so let's see. Good. So we still go on with the balancing. Now, so a chemical equation, you can be balanced either by what? Inspection of the equation. You just inspect the equation, and then when you inspect the equation, just look through the equation, and then you apply the necessary number of molecules needed to balance the various elements. Please, when you are balancing, as we saw in the video, we heard as well, do not alter the subscript. It is just the coefficient that you can change, right? If you alter the subscript, you are altering or changing the identity of the compound. So never ever change, like if you see O3 and you go and add something to it. No, when you do that, you change O3 and let's say you make it O4. You have changed the whole compound. You only write or change the coefficient. Alright, so take note of that. Good. So let's look at this equation. We have, when we do by inspection for hydrogen, at the reactant side we have 3 hydrogen atoms, but at the product side we have only 2. We have 1 sodium at the reactant side, but product side 2 Oxygen, we have 5. Hydrogen, we have said that already. So you realize that this equation is not balanced. So let's see. So we are saying that if you look through the above equation, you will find that sodium is 1 on the left but 2 on the right. Right, as I've just indicated to you. Right. Good. So in balancing, you need to put 2 before NaOH to get 2NOH. Again, this affects the number of oxygen and hydrogen as well, because NaOH has both hydrogen and oxygen inclusive. So when you change that, you have changed hydrogen and oxygen as well. So let's see. So I have my H2SO4, 2NaOH, giving us Na2SO4, H2O. What's next? I now look at it, and so number of hydrogen atoms on the left is now 4. So now I have 4 hydrogen against 2. So what do I do? If you watch the video carefully, you can tell us what to do now. So what do? I need to multiply 2 to H2O. And then when I do that, I now get 2H2O. 2 molecules of water. 2H2O. Right. 2H2O. And so when I do that, I have also altered the number of oxygen as well, because in water there is oxygen. So you see that the more you change the coefficients, the more problem you create. But don't worry, at the end of the day, you'll be successful. So now I have H2SO4, 2NaOH, Na2SO4, 2H2O. So let's see whether it is balanced or not. So I have, on the reactant side, I have 4 atoms of hydrogen and 4 atoms of hydrogen on the product side. On the sulfur, I have 1 each side, so sulfur 2 is balanced. Oxygen, I have 4 in H2SO4 and then 2 in NaOH, so it becomes what, 6. So reactants are 6. Now let's go to product side and see. So I have Na2O4, SO4, so I have 4 there and then 2 there, which is also 6. Alright. Good. So then our equation is now well balanced. It's now well balanced. So this is our new equation. This is our new equation. So take note of that. Good. So let's give ourselves this brief steps. This brief steps. So we are saying that in balancing chemical equation, write out the names of the compound first and replace them by their chemical formula or symbols. So mostly, let's assume that the word equation is given to. The next thing to do is to write the symbols or formula if it's a compound. If it's an element, you write the symbol, but if it's a compound, it becomes a formula. The next step is balance any atom first, except oxygen and hydrogen, by changing the coefficients of the compound, not the composition. That is, don't change the subscript, but change the coefficient. Please, we are saying balance any atom except hydrogen and oxygen first. Of course, there are so many ways to kill a cat, but this is what is being given. Even in the video, we saw different methods. So, as a person, just go through and choose the one which is simple for you to do. Okay. So when you look at the example, we have lithium plus oxygen, giving us lithium oxide. Now I have Li plus O2, giving us Li2O. This is an unbalanced equation because I have lithium 1 on reactant side but 2 on the product side. Oxygen is now 2 on reactant but 1 on product. So what do? I balance my lithium by multiplying 2 by the coefficients of lithium, which is 1, and get 2. When you do that, you are getting 2Li plus O2, giving us Li2O. Now oxygen is still not balanced, so what do? I need to multiply 2 to the product side, so I'll have 2Li2O, and when I do that, I have created another problem for lithium, so I need to multiply again the lithium by 2 and get 4. So I will get 4Li plus 2, so plus O2, leading to 2Li2O. And when you do that, that has become a good or a balanced equation. So I have 4Li plus O2 giving us 2Li2O, and this is a well balanced equation. So you just do by inspection and then taking inventory, and then you begin to change the coefficients. Remember, we don't change the subscript. When you change the subscript, you are changing the composition of the compound, right? Good. So these are trial questions for you to try your hands on. These are trial questions. You see, for us, anytime we teach a concept, there's a need for you to try your hands on before we proceed to a new one. Anytime we put before you a concept, we have to try you on. Please, in as much as you study, if you encounter any challenge or any comment that you have, knowledge is not found in any single individual's head. I always want to give you trial questions so that at the end of the day you know what to do, and then you really know that if you have been able to, or if you are really understand what you have learned. Okay, so try as much as possible to go through these trial questions. In the previous discussion, we looked at how to write chemical formula. Now we use that application in writing of chemical equations, and then also balancing the equation as well. So if you're able to balance the equation, then it's good for you and for me. Right, so thank you very much. We'll meet again and discuss chemical reactions. So I wish you well, stay safe, and then we'll meet again in chemical reactions. Thank you once again. This will now brings us to the end of writing of chemical formula. So please try as much as possible to study this. It's very simple, as we know, and if you're able to go through this trial question, then you can call yourself a master on the concepts. Alright, thank you very much, and I still want to insist on the protocol that our president has been always talking about. Anytime he gives our speech, even if wherever you go, if you have nothing important to do, please stay home. And if you want to go out, it's so urgent, then make sure you go with your face mask on, and then avoid touching your nose, your mouth, your eyes. Go also with sanitizers. And I say again that your life is very dear and important to us. So stay safe, and then when everything goes down, possibly we'll meet back at school and then continue our normal activities. Once again, I say thank you.